Okay, we should be live on YouTube now, and hey everybody, welcome back to another paper reading group, and this is our second beginner-friendly paper reading group. So in our last paper reading group, we looked at ResNet, and this time we're looking at DenseNet. So I think it's a good progression from ResNet onwards. So we're going to look at DenseNet this week, and let me just quickly share my screen. So I guess I'm just sharing PowerPoint right now. Please let me know in case you can't see. I'll just switch to screen now. Please let me know if there's any issues or you can't see my screen. Just close this off. We don't need that. We don't need that. Okay. So just as usual, again this week, because we're live on YouTube this time, and I don't usually monitor the YouTube chat or the Zoom chat. So if we go to 1db.me/DenseNet, so I'll just paste that in our Zoom as well. So if I just go 1db.me/DenseNet, let's go over. That brings me to the forum. So that's this forum here. And as you can see, this is the paper link. This is the blog post. So I wrote a nice blog post about DenseNet quite some time ago. And that's actually on August 2, 2020. So that's quite some time ago, more than a year. And it's going to come in very handy today. But if you're looking for a nice introduction, I guess everything I do share today, if you do go through this blog post, it will just make understanding DenseNet a whole lot easier. And you'll find in this blog post that there's also the code in PyTorch, which is the Torch Vision implementation of DenseNet. So that's been explained very nicely in this blog post as well. But of course, as part of Weights and Biases, next week, we'll be looking at DenseNet live coding. So last week, we did ResNet live coding from scratch, which was basically creating the ResNet architecture basically in PyTorch in Scratch. And I saw there was a nice comment from Vinayak. So let me just see if I can find it. Just give me one sec. Oh yeah, there it is. So Vinayak is someone I know from Fastbook as well, and he's implemented the bottleneck blocks. Last week we looked at the custom ResNet implementation, and we looked at the bottleneck block. We didn't look at the bottleneck block, but now it's on the forums. So it's on the Weights and Biases forums. If anybody wants to have a look at this problem, he's posted a problem, so feel free to go in there. But that's not what we're looking at today. We're going into DenseNet. Let me see if I can add a tag. Oh, I can't edit this. Interesting. Never mind for now. I won't add the tag. I'll add that later. But then again, we will start with DenseNet today. And I want to do things a bit differently. Like instead of just reading through the paper, I will try and explain the DenseNet architecture first in OneNote. And then when we get to the paper, things will be really easy, hopefully, and should be an easy breeze from there on to read the paper. So let's get started. As I said, this is the DenseNet paper. This is not something we're not going to start and look from here, but instead, DenseNet, I'm just going to call this DenseNet 2. This is where I'm going to scribble. So everybody's really quiet today, but if you could please post in here that you can hear me well and you can see my screen well, so I'll be at peace, or just post in the Zoom chat. I'll really be at peace and feel very confident that you guys can hear me well. So that being said, again, so last week we were looking at, when we looked at ResNet, we saw, so the one thing we saw with ResNet is like, if you have, actually, that's not how I should draw it. Let's say if I have some input, right? That's my input. And we saw in ResNet, what happens is this input at this point goes like this. And you have, and this is again, oh, look at that. That's very, make it tiny bit bigger. This is all ResNet, okay? We are not looking at DenseNet so far. So we saw there's like a residual path, and there's the skip connection, and these two things get added. So if my input is X, and this is called as F, let's say I denote that by F, then what's the output going to be here? It's called as f of x. Basically, when you pass x through residual path, that's the output. And then this is, again, this is just x. There's no change in the input. So your final output in a ResNet block becomes f of x plus x. That's just saying, like, that's just the fancy way of saying that my output is two things. One, the output of residual path, and added to the input. So we're just basically adding the input to the output. So let me just give you an example again. I'll go to my really nice written blog post from before. Oh, I already have it here. And I just want to give you an example on how this is different. Where's that VGG example? Okay, so there was this VGG architecture that you can see here. And what happens is, in this network, there's only a forward pass. But in ResNet, there's these skip connections. So let me copy paste this, and I just want to show you the difference. So everything's clear first about ResNet. Sorry, just give me one sec. I think the speakers, headphones, speakers, that should be fine. Oh, was there that sound? Anyway, so in VGG, if you have an input image, it just goes all the way through. There's no skip connections. But what ResNet does is it adds the inputs after each box. It adds the inputs. Basically, like you're adding, if there's some output at this point, then you're adding that to the block's output, and then you're doing the same thing over and over again. And that's the difference in ResNet and VGG. So let me just quickly remove that. We don't need that anymore. And now, what did the DenseNet people do? So DenseNet, again, is this architecture by Hong et al. And they're super amazing researchers. And they thought, well, I guess instead of just having, like, overall, if you think, in ResNet, you have basically lots of convolution blocks. Like these lines are just blocks. And you just have skip connections, right? This is how this ResNet architecture is in a way looking. You just have skip connections, right? That's just this. And what the DenseNet people thought would be really amazing, or what we could do, is instead of just having like the previous layer, like just the input being added to the output of the layer, you have something like this. And what is that? That's something like you have your input, then you have your stem, the usual stem. So stem is just something that will, because if the input image is too big, the stem is just something that will perform the initial convolution, ReLU batch norm, and then just reduce the size of the input. So if this is, say, 2 to 4 by 2 to 4, stem would make something to be like, if it's 3-channel, 64 by 2 to 4 by, basically 3-channel, 2 to 4 by 2 to 4, it makes something like 64 by 56 by 56. So it just makes, stem is just like common in all architectures. We saw a stem was there in ResNet as well, which was a conv 7 by 7. But anyway, we have a stem, and then what you have is like you have these convolution blocks, right? And in ResNet, you're just pretty much adding the outputs. That's what you're doing. But in DenseNet, what you're doing is you're adding for a specific layer, let's say this one, the inputs are the outputs from all the previous layers. So if this is like, for this layer, what are the previous layers? It's this one and this one. So the input to this layer is the output of this layer and the output from the previous layer. And then similarly, the output of this layer goes to both layers. Because for this block, oh, that's bad. Because for this block, what are the inputs going to be? They're going to come from all the layers. It's going to come from the first one, the second one, third one, and then finally the fourth one. So basically, there's 4 inputs coming instead of 1. Because in ResNet, what did you have? You had, like, if you have something like this, in ResNet, it's just pretty much just going like a forward pass. So you have some output, you add the input, you add them. Then this goes to the next block, then you add the 2 together. Then this goes to the next block, you add the 2 together. You go pretty much just like that. But in DenseNet, this is the main difference, and this is why these are called densely connected neural networks, because you can see how the connections are really, really dense. Because in a way, for basically there's this, like, a bit of math is like in the paper is where they say, whereas traditional convolutional networks with L layers have L connections, because there's just going to be one connection between each layer and its next layer, right? Our network has L plus 1/2 direct connections. So that's just basically a bit of arithmetic, and you can easily find out why there's that many connections. It's not important to know that there's L plus 1/2 direct connections, but what's important to know about DenseNet is that for each layer, basically, you add all the inputs from the previous layers. And that's just the main important difference in DenseNet. So figure here, this figure here is the main thing. So you have, so this is how it looks like. Basically, you have your input, then that input is called x naught. When it goes to the second block, so let's say this is the 0th block, this is the first one, second, third block, fourth block, and so on. So when the 0th block goes to the first one, not only are the inputs like this is the first block will just get the inputs from the 0th block, but what about the second one? It's going to get input from this block and also from this block, as you can see, right? So this thing is getting two inputs, one from the previous block and then from the block before. And similarly, this block is going to get three inputs, one from the previous block, one from the block before, and then one from this block. So it's like three inputs over here. And same thing over here. This is like, it's going to get four inputs. So this is the main point of DenseNet. And if there's any questions on this, because now we're just going to go and dig deeper into the details. And we're just going to look at, okay, how do these connections work? Why are there no errors? And like, why does this network still train very well? So we're just going to go into the details from this point onwards. But if there's any points, please let me know.
Hi, I have a question here.
Sure, shoot.
Say you have like 50 convolutional blocks, and in a DenseNet, as you're saying, you will get the connection, the 50th convolutional block will get the connection from the first convolutional block. I can imagine that not being very useful. So has someone looked into how many layers you should go back? Like what's the optimum number that you can go back into, like to get the inputs from?
That's a good point. I think I see your point when you're saying like in the 50th block, if you have the first block, which is the really early, layers. But this architecture, this network architecture just says the complete opposite to what you're mentioning. So like the intuition in this architecture is that it is useful to use the first block. So now I guess what you're trying to say is, in a way, you're trying to disagree with the researchers, or not quite, but then this is again a new line of research that I don't know of. I don't think, at least that I don't know of, is like there's no such hybrid architecture that looks like DenseNet where the connections go only like 10 blocks before, 15 blocks before. So if there is any, I don't know about it. But again, the DenseNet architecture just makes the completely opposite point, where they say that it's actually very helpful to have like all of these connections. But again, the way the DenseNet architecture has been designed is different to this image. So so like in this image, what you're thinking is like, okay, if you have this 50th block, then all of these get added. But when you look at the actual implementation of DenseNet, you'll see that there's some slight differences, and those slight differences actually make a big difference. So as we go deeper, I hope that this thing will become clearer on how DenseNet is still a good architecture.
I see. Thanks.
No worries.
Actually, I would like to add one thought in it. Again, from my understanding of this paper, it doesn't connect 50 blocks. It is only within the dense block. So there is transition blocks right after these dense blocks, because you cannot have 50 blocks with same feature map. That will kill your memory, right? So
Ramesh, we're jumping forward. That's something I was going to come to. I think that's a great point, but I was going to come to that slowly. So let's not go down that road just yet. Hello?
Yeah, that makes sense. I was just trying to say that, you don't need to worry about 50 blocks. Nobody does 50 blocks of DenseNet.
Absolutely. So I guess that was just the next point, but now that Ramesh has mentioned it, the way this the dense architecture, but actually before we go to that point, something I do want each and every one of us to think, and maybe just come to the forums and point an answer, or think of an answer, at least in your head, and just spend like 30 seconds thinking about this, is like my input is going to be something like, usually it's like 1 by 3 by 2 to 4 by 2 to 4, right? What does that mean? 2 to 4 height, 2 to 4 width, 3 channel, and single image. And then by the time you go down and down, right, you end up coming to a point, for example, where this becomes the last output. Because if you see VGG, which is here, as you can see, when you start with 2 to 4, when you start with 2 to 4 by 2 to 4, and you keep going down and down, you end up reaching a point where your feature map size goes down to 7 by 7, but the number of channels goes up. So the number of channels goes up to 512. So now the question is, I guess, how do you make sure that when you get to like when you get to that point from like 3 by 2 to 4 by 2 to 4, and you get to this point of like 512 by 7 by 7. So like, how do you make sure that these two can be added to each other? Because that's what they're doing, right? That's like, this is the connection. And that connection basically just means like adding or concatenation or like some kind of joining of the features. So I guess the question that I want every one of us to think and spend 30 seconds on is like, how is this even possible? Like, how do you join this with 512 by 7 by 7? So that's just something I want each one of us to think for a second, and then I will share the solution. So then what they actually, let me just bring up what they do differently to make sure that something like this happens. Is okay. So what you then so then if we go through let me just go back to the paper. All right. So then what you see, in fact, is, and we're going back to what Ramesh was mentioning, is that the way the DenseNet architecture has been implemented is slightly different from how we understand it in that one figure right now. Simon said using 1-by-1 cons, which is definitely a good point, because we are going to use 1-by-1 cons to make sure that the number of channels is same, or the feature map size is same. But the way the researchers do this is using this figure 2. So let me just copy paste this in OneNote. Okay. So sorry, give me one sec. So then the way the DenseNet architecture has been implemented is different. Sorry about that. Is different from this image that we saw before. The actual implementation looks something like this. You pretty much have, in the DenseNet architecture, you pretty much have something called a dense block. And when you start with, say, 3 by 2 to 4 by 2 to 4, and you do your stem, which is your initial convolution, and say you end up at something like 64 by 56 by 56, because that's what the stem does. A stem basically increases the number of channels and decreases the spatial dimensions, right? And then what happens is, inside the dense block, which is this dense block here, inside the dense block, the size of the feature map in a way remains the same, but like it remains 56 by 56. But what you do is, this is where all the concatenation can then happen, right? Because now if the feature map size is the same, then you can concatenate features to one another, right? So if it's all 56 by 56, and then basically you have some number of channels, then you can concatenate with one another inside the dense block. So this is the actual concatenation just happens inside dense blocks. And this feature map size remains the same. Only the number of channels goes up, and it grows exponentially. Like, not exponentially, basically it just grows by a factor called growth rate. So what happens is, let's say we go from dense block 1, and now the output is something like 256 by 56 by 56. Let's say that's the output. Then you have this convolution and pooling, which is what is called something like a transition block, which is exactly something that Ramesh already mentioned as well. Is like, there's this thing called the transition block. And what transition block does is, it does something very similar to the it does something very similar to this VGG architecture. Because as you can see, in convolution neural networks, what happens is you start with the big spatial size. And as you keep going forward and forward into your network, the number of channels keeps on going up, but your spatial dimensions keeps on going down. So basically what that means is when you start by 2 to 4 by 2 to 4, which is like you have a big image, but you only have 3 channels. By the time you're towards the end of the network, you end up being like 7 by 7 by 512, which means you have 512 channels, but your image size has just gone from like 2 to 4 by 2 to 4 to 7 by 7. So this is now the feature map. So the feature map has reduced in spatial dimensions, but it has increased in the number of channels. And what this transition block does is it does something very similar, is like it will, because it's a convolution and pooling, what it does is it halves my spatial dimension size. So what you get from here is something like, I can't remember if it changes the number of channels. That's something I'll have to just confirm, but it definitely makes my spatial size half. So then you have 28 by 28. Actually, it doesn't change the number of channels as far as I remember. So it's like 256 by 28 by 28. And then again, in this block, you just keep going and going onwards. And then you get to a point where you have like something like 512 channels this time, 28 by 28. So as you can see, as we are progressing through this DenseNet architecture, we're also following this common approach of like, we started with 3 channels. We started by 2 to 4 by 2 to 4 spatial dimensions. Then our channels got up to 64, spatial dimensions got reduced. Then this transition block reduced my spatial dimension further. So it got down to 28 by 28. And as I keep going through the dense block, my number of channels is going up. So as I'm going into and deeper into the network, instead of having 3 channels, I have something like 512 channels. And instead of having a spatial dimension size of 2 to 4, I have a spatial dimension size of 28. And this is a good and important point to keep in mind, that DenseNet does something like completely the opposite of what the common norm was. And remember, again, I think this was a paper written in 2015 or 2016. This says the first version came in 2016. So again, that's like 5 years ago, and a lot of things have changed in 5 years. But again, because this is a beginner friendly paper reading group series, what we want to do is we want to get the basics right first. So the main thing to note here, or the main thing to understand here, is the common architecture design is like you increase the number of channels and you decrease the spatial dimensions. And that's something that's happening inside the DenseNet architecture as well. And then what another thing is happening is like the dense block. The dense block in itself is where all the concatenation of like the main point in the paper was mentioned is like for each layer you have the outputs from each of the previous layers. So all of that is happening inside the dense block. But otherwise, the architecture is like the features go from here. You pretty much get the output at this point, then you get the output at this point. So you get the output here, you get the output here, then you get the output here, then you get the output here, and the output here. So in a way, like this is again a very forward pass. Like things are just being passed from previous layers to next layers one by one. But inside the dense block, things are a bit different. Inside the dense block is where all the concatenation of the features. Inside the dense block is where your last layer basically has all the features from the previous layer. So this is how this is a bit different from figure 1, which was this one. So this figure essentially gets the main idea of the DenseNet architecture, but this figure is where the implementation details start to come in. So if there's any questions, please also keep posting on the forums. I'm assuming there's no questions so far. So that's the main implementation thing that we need to be careful of when we look at DenseNet. And we will look at the implementation next week. Again, when we look at next week, we're going to build a dense block. We're going to build the dense layers. We're going to build all these connections from scratch in PyTorch. But if you want to skip ahead, if you go to that, again, if you go to that blog post, you'll see like all these things have been mentioned. And something that's now I'm going into basically just words, or basically like what researchers call these different things is, again, this has been mentioned that this is dense block. So that's something we know, that the blocks where all the concatenation of the previous features happens have been called dense blocks. And then these blocks, or like these bits, are called transition blocks. Okay. So overall, if you look at the DenseNet architecture, it looks something like this, right? If I call them layers, like instead of calling them blocks, if I just call them as layers, you have something like this. Your input image, which is this one, passes through a stem. So I've missed a stem in this this is just a simple view inside my, oh, sorry. This is just a simple view inside my dense block. So I have my dense block like this. So in this dense block, you can see, depends on how many layers there are. So in this dense block, you have 1, 2, 3, 4, 5 layers, just in this example. So what you can see is like, now again, the question is like, okay, I understand that dense blocks is where the concatenation of the features happens, and dense block is where, and transition blocks is where the transition happens, that is the spatial dimensions become half. But what exactly goes on inside like this dense block is basically, as you can see here. So you have an input image, as you can see here, you have an input image. You go through layer 0, so the input image is input into layer 0, and it produces an output, which is this gray output. Oh, sorry, the gray output is the input image and produces an output, which is this purple output. And then the layer 1 accepts not only this purple output, which is from layer 0, but it also basically accepts or gets this gray input image. So you can see like layer 1 is not only getting layer 0's output, but also the one layer before. And similarly, when we come into layer 2, it gets layer 1's output, which is in orange. It gets the purple output, which is layer 0's output, and gets this gray output, which is again the input image. So that's basically what's happening is like you're concatenating, like you're not inside the dense block, you're providing information. So the way the researchers actually quote this or explain this is like ResNet is thought to be in a way, if you think of it, ResNet is something that just passes state. So in ResNet, what you have, could I please ask everybody to mute themselves if you're not? My Zoom decided to quit unexpectedly. Can you guys hear me still? I'm really sorry about that. Could you please just post in the chat that you can hear me? Okay, excellent. There is no screen being shared. Yes, I think I'm not the host anymore, am I? It's just giving me some stupid errors. One sec, let me just correct this. There's some thing weird going on. Okay, we're back. Can you guys see my screen now?
Yes, it's visual.
I was just explaining like this dense block architecture, and I've actually lost my train of thought on where I was. But let's now see the exact specifics. So I will go into the paper at the very last. I just want to spend the next 10 minutes just explaining all of this, just explaining like how this could be. Like, I want you all to like, because this is a beginner friendly, I want to be as beginner friendly as possible. So I want to explain the shapes. I want to explain like how these things go on, or like what's actually going on. So let's first understand, so let's just draw semantics. Like, let's just draw blocks to explain things, right? So you have the overall architecture. We'll start again in a top-down approach. We'll start understanding the DenseNet architecture first, then we'll understand the dense block, and then we'll look at the dense layer. So let's just start. So you have an input image. Let's say this is my input image, 1 by 3 by 2 to 4 by 2 to 4. Again, it goes through the stem first, right? The stem. Which is again a very common thing in most architectures. The stem just does, it just reduces the number, it just increases the number of channels and reduces the spatial dimensions. And then it goes into like what I like to call DenseNet. So let me just call that DenseNet here. Now this DenseNet architecture, if you think of it like overall, all of this is the DenseNet architecture, but I'm just trying to like in a way, I'm just like trying to make sure like you think a little differently from the paper, but I'm just trying to explain things in a nicer way. Then this architecture, actually, instead of calling it DenseNet, let me just call them dense blocks, or let's just call them blocks. Okay. So this overall thing is the DenseNet. All of this in like dotted lines is the DenseNet architecture. So you have your input going through the DenseNet, you get some output, which is like, say, 1 by 1,000, which just means like it's able to classify into 1,000 classes. But then these blocks, and these blocks are, these blocks look something like, I'm just trying to show you this image again, so you remember, these blocks look something like this. Here you have basically dense block followed by a transition block. Then you have a dense block followed by a transition block, and so on. So you have dense block 1, transition block 1. Then you have dense block 2, transition block 2. Does that make sense so far? And basically you have like four of these. So all the way to something like db dense block 4, transition block 4. Okay. And inside the dense block, it looks something like this. So inside the dense block is where you have, let's say, however many layers you want. 1, 2, 3, 4, 5, 6, let's say. This is where all of this is happening. So you have your input being passed here, then this goes to this one, this goes to this one, to this one, to this one, and this one, and for example, and then this one from the second one. Basically, this is where all the concatenation is happening. And like all of that, you get the point. Like inside the dense block is where this concatenation is happening. So as you can see, the overall architecture can be thought of to be in like 3 levels. This is the first level, this is the second, and this is the third. So this is the way how I like to think of architectures from a top-down perspective, because now I think DenseNet becomes a lot more clearer in our heads. So you have your input, you get your outputs, it passes through a stem. Now you have blocks. Blocks means dense blocks and transition blocks. So dense block is here, transition block is here. I haven't explained what a transition block is. So a transition block is just a 1-by-1 conv followed by a pooling layer. So what it does is, what does a transition block do? If you have, say, if you have a transition block here, and you input something like 1 by 3 by 2 to 4 by 2 to 4 to a transition block, it will give you an output of 1 by 3 of by 1, 1, 2 by 1, 1, 2. So it basically halves your, makes your feature or your spatial dimensions half. So it makes your feature map be the half size. So that's what transition blocks are doing over here. And what's happening in dense blocks? In dense blocks is where all this, there's like these dense layers inside, depending on however many you have. So if you look at the various architectures of DenseNet, I just want to show you how this looks like. So you can see you have, as I said, you have 4 dense blocks and 3 transition layers, sorry. So you don't have this one, right? You have 4 dense blocks and 3 transition layers, and you can see like each architecture, like DenseNet 121, DenseNet 169, DenseNet 201, and DenseNet 264. What's the difference in them is the number of layers inside these dense blocks. So dense block 1 has 6 of these in all of them. So dense block 1 has 6 layers, as you can see, cross 6, cross 6, cross 6. But in DenseNet 169, dense block 2 has, again, all of them have 12, 12, 12. But you can see in dense block 3, this is where the difference is in 121, 121, and 264, is that you have 24 layers in dense block 3, 32 layers in DenseNet 169, 48 in 201, and 64 in 264. So you can see how like these architectures, now you can see like, okay, 264 just means that dense block 3 has more number of layers compared to DenseNet 121. And then I've already told you what a transition block looks like. A transition block is just a 1x1 conf followed by a pooling. I haven't told you what this dense layer looks like. So if you look at the dense layer, it just looks something like this. It's a 1x1 conf followed by a 3x3 conf. That's it. It's like a bottleneck. It's like a bottleneck. It's like a bottleneck design. So basically, if your inputs are, say, let's just take this example. What are the inputs going to be for my DB1? So you pass in, I'm just also showing you like what the feature map shapes and sizes would be. So let's say if my input is 1x3 by 2 to 4 by 2 to 4, what's the stem gonna do? It's gonna give me an output of 1 by, say, 64 by 56 by 56. That's this. So this input to the dense block 1 is 1 by 64 by 56 by 56, which means the input over here is 1 by 64 by 56 by 56. So that's this. So then in my dense layer again, my input is 1 by 64 by 56 by 56. And then what this 1x1 conf does is that it first changes like this number of channels to some, because it's the bottleneck design. So what's different in bottleneck designs is that you first increase the number of channels or like set them to some number, and then you put them back to what the number they're supposed to be. So this will go from 1 by 64 by 56 by 56 to 1 by 128 by 56 by 56. And then this 3x3 conf will put it back to 1 by 32 by 56 by 66. So what's happening is like each of these layers are adding plus 32 features. Each of these layers are adding plus 32 features. So by the time, I will again explain how they're adding plus 32 features, but by the time you get your output from my dense block 1, instead of like this being 1 by 64 by 56 by 56, it's something like 1 by 256 by 56 by 56. Now, why have I made all of this so complex? Or like, why am I showing you all of these shapes or numbers? Is like, if you really want to understand an architecture, you really need to understand what's the input shape, what's the output shape, and like, how do these things look like? Like what I could have done in an easy way is like just gone through this research paper and then shown you, okay, DenseNet, like dense blocks are basically like DenseNet is just this, where inside the blocks is where you concatenate the features, and then transition blocks is where you reduce the feature size. But you would never understand like the devil is in the details and the complexity is in the details. So you would never understand to look at the DenseNet architecture in this way. And what would be missing are the details on like how do basically these features get concatenated in all those details. So I'm just going to take questions now.
Hi, Aman. Can you hear me?
Yeah, could you please post them on the forums if that's okay?
Okay, sure, but it is quite verbose. That's why I thought.
Your just your voice is cracking a lot. That's why I just said post on the forums. Thanks. I'll answer this one, Durga. How 32 features are getting added. So let me answer this one. So where are we? We need to keep size impact with padding while doing convolution. Yes, that's correct. Inside the dense, basically inside the dense blocks, you do have enough padding to make sure like if the feature map size is 56 by 56, it doesn't go up or down. Stride with the re-strided 1x1 convolution. Okay, so you were just trying to answer, I guess. What's the reason intuition? It's just a difference of the intuition is like deeper architectures. When we get to the efficient net, you will see like there's different ways of scaling architectures. And one of the easiest ways to scale architectures is just to make them deeper. And that's just the intuition is like if you have deeper architecture, then they can learn more complex patterns, or they can learn more complex things. And that's why they can perform better at ImageNet, or they can perform better at different data sets. That's just the intuition here. So in DenseBlock 3 and 4, you just have more number of layers, because what we want to say is that DenseNet 264 is deeper than DenseNet 121. So I was taking this question of how 32 features are getting added in DB1. So as you can see, what happens is, I'm just going to go into the details, is like when you start with 1 by 64 by 56 by 56, and dense layers are all 1 by 1 conf followed by 3 by 3 conf, what it does is, this is pretty much just outputting things of 1 by 32 by 56 by 56. So this the first layer outputs, this is all a mess. So the first dense layer outputs are this shape, 1 by 32 by 56 by 56. And then what you could do is you could concatenate them together. So you have 1 by 96 by 56 by 56, which is what is going into the next layer. So this is what goes into the second layer. And then in the second layer, it again goes from 96 to 128 channels back to 32 channels. So the output from the second layer is also 1 by 32 by 56 by 56. Then you concatenate the two together. So you have something like 1 by 128 by 56 by 56, and so on. By the time you reach the end of the dense block with 6 layers, your output shape becomes this 1 by 256 by 56 by 56, because you're just concatenating 32 channels every time from the outputs of the dense layers. No, this architecture actually does not overfit. I think in a way it does overfit slightly more than ResNet, but I haven't done any research on. And from the paper, there isn't any, as far as I know, there isn't any straight connection. Of course, it has. I will go into the details of this one. I will just share some text that has been mentioned in the paper. I'm confused on 1 by 1 with 128 filters as bottleneck. Is that the same across all box and all the layers in each box? Yes. So all layers, at least from an implementation perspective, when you see, again, this is something that's not mentioned when you read through the paper. Let's keep going, and I will show you in the paper, but this is the bottleneck layer. Although each layer only produces K output feature maps. So K in this case is 32. So K is this growth rate. So what they say is basically, because in a dense block, what you're doing is your features are growing by some factor, which is plus 32, right? So this plus 32, I just said 32 because I know that the growth rate that they've used in DenseNet implementation is 32, but actually they just say like it's called K. And then it says, it has been noted that a 1 by 1 convolution can be introduced as a bottleneck layer for each 3 by 3 to reduce the number of input feature maps. So basically, what they do is so the 3 by 3 convolution that has more computation than a 1 by 1 convolution. So the fact that 3 by 3 does not act on a feature map which is too large, what they do is you have a bottleneck design. So the 1 by 1 conv reduces the feature map size, and then this reduced feature map size is what gets passed to 3 by 3. So you will find those details in this bottleneck layers. So in our experiments, we let each 1 by 1 convolution produce 4K feature maps. What that means is, because I told you already K is 32, what that means is that for all of these layers, 1, 2, 3, 4, 5, which look like this, for 1 by 1 conv followed by 3 by 3 conv. For all of these layers, the 1 by 1 conv has 128 channels. So that's fixed. So more questions? Ramesh, could you maybe reply to this comment and just make sure, I just want to make sure that this has been answered. In the transition block, could we only have the pooling layer and avoid the 1 by 1? What is the advantage of where we go from 64 by 56 by 56 to 128? Oh, that's a good point. But basically, like these are all these experiments. And when I do live coding next week, I do want to answer all of these experiments. Like what we can do is we can try, I guess like the question, the way I answer these questions is by trying and testing. So try removing the one by one layer, because this is like, there's a reason the researchers would have. So going through the experiments section over here, and basically they also ran a lot of experiments on like different learning rates on different things and different stuff. But try, when I do show you how to implement the DenseNet architecture from scratch next week, then take that architecture, implement it as is, and then remove the one by one convolution and see if it makes a difference. Fundamental doubt, how do you differentiate between filters? Okay, how do you differentiate between filters? Like each kernel is unique in a stack of kernels and filters. So when the channels depends on number of filters we apply, how exactly we differentiate. Since number of kernels will be equal across filters, I'm not sure I understand. Yeah, I'm not sure I understand this, Durga. I'm really sorry. I'll read it again. Yeah, I'm not sure. I really don't know. Awesome. Great you like that advice. Fundamental question. When we go deeper with layers, the features that get extracted are called low-level features or high-level features. They're called high-level features. So the low-level features are the ones that are in the early layers, and they're called low-level because it's just basically like this paper visualizing neural networks, I think. Zeiler and Ferguson. Oh yeah, here it is. So just to answer this question on like what is a low-level feature and high-level feature, if you look at this paper, visualizing it, and this is something we've discussed in one of our past sessions. When that opens, I'll come back to that question when that opens. I'll just take more questions so far. Okay, here's the question from the ResNet architectures also add skip connections. DenseNet also adds connections from early layers to later layers inside the DenseNet blocks. Yes. How do you form your intuition about how this is helping the overall performance? How do this kind of skip connections improve performance over the vanilla ResNets? That's a good point. So the point that the researchers make, actually, let's read through the paper now. We're at that point where instead of like asking me, let's read through the paper. So the point that, where is it written? These are the points that they make. So this kind of architecture has several compelling advantages. They alleviate the vanishing gradient problem, strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. So I know that's very counterintuitive, like how does this reduce the number of parameters? But something that they're saying is like, it encourages feature reuse. So what that means is, once you've learned, like once your earlier layers have, for example, once this X1, and this is my intuition of reading this, is that once this X1 has learned the features from X0, then these features in green don't have to be relearned. Like they get passed to all the later layers. So these later layers don't need to worry about like the features that are being learned in the earlier layers. They just have them as part of their concatenated input, right? So this is in a way encouraging feature reuse. Is like, it's much easier now for the network, because again, these are low-level features in the beginning, and then these are high-level features at the end. So at some places, it might be helpful to know what the low-level features are. And my intuition is, like in this network, what you have is, if the network basically at X4 wants to look back in the previous layers at like X2, X1, X3, it has the ability to do so very easily. Whereas in ResNet, because you keep adding your outputs in a way, it's like a state, right? So think of it as like, 5 people are standing in a queue. So think of this, like the best example is 5 people are standing in a queue, right? This is your deep learning network. Let me just try and make this example very clear. Oh, this is really bad. So let's say 5 people are standing, or let's just say 5 people, right, are standing in a queue, and you have a ball here. Now, what each person does in ResNet is that they update this ball, so it goes from red to blue to black to some other color, green, and then it goes to maybe orange in the end, and finally some other color, light blue. And this becomes your output in the end. But what each person is doing is like they're adding their own information on top of the previous person's information. Whereas in DenseNet, again, if these 5 people were to pass some information, if the later layers need to look at the first layers, then they need to find like that information is still in this orange ball, like in a way, because it got updated from red to orange as a process. But for this person in DenseNet, it already gets the red ball here, like that red ball gets passed. So this is the main intuitive difference in DenseNet and ResNet is like you can always look back and you know what the earlier layers have learned. And I think in that way it makes the overall architecture an advancement over ResNet. But that's just my intuition. I could be like completely wrong. Could you please explain quickly how a one-by-one conf? Oh, you're saying that also happens in one-by-one skip connections, but I'm talking over the overall architecture. In skip connections, if you have a network that's just being skipped, it's just around that person. So like the skip connection in this case is just from here to here, but like all the way, like this is then going past and then there's a skip connection, and then this is going to get passed and then there's a skip connection. But in DenseNet, you have this input being passed all the way. So this like the connection is much easier is the point I'm making. Are there any application studies done for DenseNet? Like how do we know which connections inside the dense block? I'm not sure of are there any application studies, but I guess as part of this paper reading group, my point is, or like my main goal was to make sure that the audience understands what DenseNet architecture is and how it is different from ResNet. And as far as that's been accomplished, I'm going to be a happy person that that's happened. So in terms of like ablation studies now, there's a whole lot of ablation studies that we can do. So before answering more questions, yes, pretty much. Like that's my intuition, Vinayak. That's pretty much my intuition on this. Absolutely, this is exactly the point that I'm making as well. So like the summing and the concatenation is the difference, which is like exactly as I was saying in the red ball being updated, because each time you sum something, like add something, it gets updated to a new value. But if you concatenate it, then that previous value just remains all the way towards the end. Now, let's just quickly, I've spent all the time in explaining DenseNet paper without reading the DenseNet paper. So let me just go through the paper and show you like how now this discussion is going to make, like the ideal thing that you could do now is go back and read the densely connected network, and hopefully it will make things very easy. So the main points here are, okay, this is what a dense block looks like. And then they say instead of having L connections, you have L plus one. Actually, let me just go here. So the main points I'm just going to go skip through so you understand this paper, is like the main point that they make in introduction is instead of having L connections, you have L plus 1 by 2. And then there's several advantages like vanishing gradient problem, encourage feature reuse, and reduce the number of parameters. And then we know the dense block looks something like this is where, and the overall architecture. So if you keep reading through here, they say deep learning in 2016 came a long way from these previous papers, Linet, which consisted of 5 layers, VGG, which consisted of 19 layers. And then they say, okay, ResNets were introduced, which could take as up to 100 layers. And then now they're just talking about like these, the the ResNets, and they say like something that's really common is that they create short paths from early layers to later layers. And this is like the researchers trying to develop that intuition. It's like they're looking at things and they're like, okay, skip connection is basically just a short path from input to output. Like, so the you basically just add the input to the output. So what you're trying to do is like you're adding short paths. And that's something exactly that stochastic depth does as well. So if you don't know what stochastic depth is, just go to 1db.ai slash AARORA, which is A Aurora, and you'll find this article revisiting ResNets, which I've written about NF, which basically ResNet RS. And in here, I think there should be something about stochastic depth. There it is. So I've explained exactly what stochastic depth is over here, and that's not something I'll discuss as part of the paper reading today. But please feel free to look at that there. And going back to the paper, so the main point that the researchers are trying to make is like, okay, what they're trying to do is they're trying to create paths from early layers to later layers. This is the key point to note: paths from early layers to later layers. And then this is where they say we propose an architecture that distills that insight into a simple connectivity pattern. So to ensure maximum information flow between layers, we connect all the layers. So this is the main intuition. Is like this is how the researchers thought. It's like if we connect all the layers, then it's going to be the maximum information flow. And to preserve the feed-forward nature, which as I've said, is just means like the spatial dimensions come slower and the number of channels goes up. It just says like you have things divided in dense blocks, and then you have LL plus 1/2 connections. And therefore, this is called as a densely connected network. And keep going. I guess I just want to highlight the main thing so you can go back and read this paper, and it should be all very easy for you. I usually skip over the related work, but if you're new to deep learning, do go over through the related work as well. And then this is where they start explaining DenseNet. So they go, okay, ResNet looks something like this, which is f of x plus x. So as you can see, if x is xl, so my output is just my previous output, and then f of x of previous, basically input passed through the residual path plus the input. And then I've already said, okay, what's the difference in dense connectivity? So in dense connectivity, you have something like this, where you have like the final layer has all the inputs concatenated. So that's why it's represented in maths like this. So instead of having like just the one layer before, you have like all the layers before. It says pooling layers, which is they're just saying like, okay, pooling layers, I've already told you what they do. They just pretty much reduce the feature map size. Growth rate. So as you can see, what's going to happen in this case is like, actually, this is explained better in that image that I have. So as you can see, each layer in a dense block adds its own features, right? So the number of features are growing. The rate by which these features grow, or basically the number of channel outputs from each layer, is referred to as growth rate. So don't be confused by growth rate. It's basically just 30. It's just basically 32. Yes. And then again, we've already looked at this. Now you know like what the differences in various DenseNet architectures look like. So basically, in 24, there's basic differences in DenseBlock 3 and 4, and DenseNet 201, 264. All of these are just deeper versions of this. So it's just scaling basically. Again, bottleneck layers, this is something I mentioned. So in bottleneck layers, you go, you have a 1x1 followed by a 3x3. Bottleneck layers were first introduced in ResNet. And you can say, here it is, a 1x1 convolution can be introduced as bottleneck before the 3x3. And that's pretty much it. That's just DenseNet. And then there's like implementation details. So I've kind of explained everything. So they go, okay, we use a kernel size 3x3. We use 1x1 convolution followed by 2x2 pooling as transition layers. So this is just everything that I've explained in. This is everything that I've explained in this diagram. So when I was explaining like blocks, dense block, dense layers, this is just pretty much it. And I guess that should be it. And then there's just some experiments that you can read through on the experiments that the researchers tried. The training pipeline, basically, that's however many epochs we trained, what was the learning rate, 90 epochs, what was the momentum. So these are things that are just very common. And finally, this share like which data sets they've got. They share the classification results on ImageNet. So there's not a lot going on. I do like the discussion per se, but I'm going to skip. So if you go back and you read this, and there's like this really good discussion on feature reuse, which just says, okay, why having these dense connections is actually better. So for everybody asking me those questions, have a read of this feature reuse part, and then finally there's a conclusion. So in this, they say, okay, we proposed a new convolutional neural architecture, which we refer to as DenseNet. And that's time, basically. This is all that I wanted to cover today. Could you please, oh crap, I missed this. Sorry, Sangam, I missed the zooming in. Okay, I guess thanks very much. I hope I have explained DenseNets well, and I hope you do understand DenseNets now. So question is, why does increasing the number of layers help? It's just, as I said, for the whys, try it. Try it, experiment with it, use weights and biases for your experiments, and experiment. You will see why. Like, develop that intuition on why. Like, I don't have an answer because these are things like this. If I want to give you an answer, like I'll probably point you to a research paper, or like I'll mostly just say, okay, this is how these things are done and this is how it works. Because if you do it the other way, accuracy actually decreases. But for those things, like these kinds of things, just try, like just remove the convolution and just use a pooling layer, or just like try like going from, I guess the question you're asking is like, why do the earlier layers have to be 6 and 12 and then followed by that? The answer is, in my head, the answer is because in the earlier layers, the feature map size is too big. So if you have too many, number of layers early on, then that just means that a lot of computation is already happening and you're just adding more and more computation. So your network is actually becoming massive, and it's just becoming massive in terms of memory. But by the time you reach dense block 3 or dense block 4, your feature map size is reduced in size. So it's gone from 224 to something like, I don't know, 14 by 14. And then it's much easier to have a lot more number of layers then, as opposed to like having a lot more number of layers when your feature map size is 80 by 80 or something like that. So that's just my answer, but have a look and try and finding this answer for yourself. Oh yes, of course. And the paper live coding session for DenseNet will happen next week. Excellent. I'm glad, Ravi, that you're keen. The first layer has only 32 outputs, so the 1 by 1 is not a bottleneck as it increases. But yes, that's the point, Ramesh, and that's something I have my qualms against. And that's something I was against it. So when I was implementing, actually, let me just show you this. Where is this? Why is this notebook not open? So just before this, I was actually implementing things from scratch. And like, this is how a dense block looks like. It goes from 64 to 128. Like, that's actually increasing the number of layers. And by the time you reach, like, as you can see, this 128 is pretty much fixed. But for the later layers, you go from 352 to 128. So that's your bottleneck. You go from 288 to 128 and so on. But like, I don't like this number of 128 being fixed. That's something I don't like. But again, there must be a good reason on why researchers have done something like this. So like going from 992 to 128 channels, like you probably would be losing a lot of information in doing something like this. And then you go from 128 to 32. So that's a really, really good point that you've raised. But I hope in like showing you this little implementation, like these are things, look out for these things, and I'm so happy that you are looking out for these things, because I also try and look out for these things. Excellent, Vinayak. I'm so happy to hear that. That's great. Thanks for that. Sorry, I don't know what your Naveen, thanks for that, Naveen. Cool. Let's stop it here then. Thanks very much, everybody, and I will see you next week when I live code DenseNet from scratch. Bye, and hope everybody has a good week.